The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Introduce Kevin Aswegan, Magnusson Klemencic Associates in Seattle. He's a design engineer, and he's going to talk about trends and demands for concrete performance-based seismic design towers.
Thank you for the introduction. Today I'm talking about the topic of trends and demands for concrete performance-based seismic design towers. I realize that's a pretty generic title. You probably weren't able to guess what I'm actually talking about, which is actually building on Tom's presentation of shear and moment amplification of MCE demands relative to code-based designs. So I am presenting a study that I did with a colleague of mine, Ian McFarlane, both of us at Magnusson Klemencic Associates. He's actually sitting a few rows back, so if you have any really difficult questions, you can ask him at the end. So to start with, what do we all love? Designing things, right? That's why we're engineers, that's what we're really good at. That's what we like to do. So what do we all not love? Redesigning things. This is at the heart of what I'm presenting today, which is the topic of MCE analysis and the uncertainty associated with trying to predict MCE results from DE results. This will help us avoid redesign. It's useful for all parties involved because you can get a really good estimate of the proportioning of the building early in the design prior to completing the actual MCE analysis phase. So what do we not like? Redesigning things. So that's what made us start thinking about this study of looking at what are the actual amplifications from DE to MCE and SLE to MCE for both shear, but not only shear, also moment in core walls. So first I'm going to talk really quickly about introduction and motivation for what we are working on. Quickly go through the database of results that we put together, the results that came out of that, and then a quick case study, conclusions, and some time for questions at the end. So I don't think I need to give a real introduction to performance-based design. That's been gone over by a few of the other presenters, but it's fairly young. It's been around for about 20 years or so. The first building that MKA designed using PBSD methodology was about 20 years ago in Bellevue, Washington. It has since increased quite a bit in popularity to the point where virtually every building on the west coast of the United States is designed using a performance-based seismic approach. Every tall building, that is. It has a lot of major benefits. The elimination of structural height limits, the elimination of the backup moment frame, and of course better understanding of building behavior. But it has one really big drawback, and that is the uncertainty associated with predicting the MCE results from the linear code checks and from the SLE check. Typically the SLE and the DE checks are pretty easy. We do them quick and early. We don't actually perform the MCE check until later in the design process because it does take a lot more work. We like to have the design as set as possible before we do that. And for that reason, there can be some unpredictable results that come out of the MCE phase. So we set out to try and reduce those unpredictable results. So our motivation came from a few different sources. One is we know from experience that designing for DE and SLE alone is not adequate to safeguard performance under MCE loads, especially, for example, for core wall shear. As Tom pointed out, the amplification from DE to MCE is not 1.5, as you would expect based on the hazard. It's actually greater than that. So the question is, what can we do early in the project? And what we typically do is we take the DE results and we amplify them by 2.5 or 3 or something like that. And we try and get as close as possible. The best way that we can reduce this uncertainty in the prediction of the MCE loads is by by studying, looking at past projects and seeing what the actual amplification has been. By doing this, we can cut down on this design by trial and error, and we can also make the MCE process truly a verification process rather than a design by trial and error. And then the third motivation for us is that we've done a lot of these PBD projects, so we have access to a pretty large database of past results, and we can mine data out of there to use for the study. So this shows you just some performance-based design number of projects that we've done over the years. Going back to the mid-90s, we were doing just 1 or 2 projects a year, really up until 2012 when it really took off, and we as a company have been doing somewhere around 6 to 10 performance-based design projects per year for roughly the past 5 years or so. So the filter that we applied to the projects that we've done, we looked at projects only on the US West Coast, so we eliminated any international projects because they typically have a different design approach. We looked only at projects from 2014 and on, just to get the most recent results. And we only looked at projects that have peer review sign-off. That way we can be confident that the numbers won't change due to a peer review comment or any further analysis. So when we applied all those filters, we came up with 14 buildings. They ranged in height from roughly 300 to 600 feet, with an average height of about 450. The locations were Seattle, San Francisco, Los Angeles, so typically US West Coast. If we were to add buildings, we would add some buildings from Oakland that we completed recently. Building use is typically residential, office, or hotel. This is consistent with what we see being constructed on the West Coast. Site class C or D. And ground motions, we actually have a pretty even split in ground motions between CMS, not CMS, 7 or 11, and whether the ground motions are spectrally matched or amplitude scaled. So for each of these buildings, we calculated the MCE divided by DE and MCE divided by SLE results. For example, the building 1 out of 14, went into the calculations packages, we pulled off these results, and for the X direction MCE base shear, it's 20,400 kips. The SLE X direction base shear was 4,450. So dividing one by the other, the amplification factor is 4.58 in the X direction. Similarly, you can look in the Y direction, it's 4.07. For this particular building, we just averaged the two together, 4.33. So when I talk about MCE divided by SLE amplification factor, it's the average of the X and Y direction for the building in question. And that's the one value that we assign to each of the 14 buildings. We did that for base shear and moment for DE and SLE. So each building has 4 amplification factors. Now I know you probably can't read this table. That's okay. I'll read it all to you. Just kidding. This table is in the paper that'll be published a little later. You don't really need to review it all right now, but each of these columns is the base shear in X and Y for SLE, DE, and MCE. And this is the table we use to generate the amplification factors. Okay, similarly, this is overturning moment. This is not the right label. This is the right label, overturning moment. We collected the same exact results for the same buildings, just looking at the base moment, trying to glean any information we could about what that amplification factor would be. This is most important for proportioning your foundation system based on DE or SLE demands. So these are the actual results. This is the base shear amplification factor plotted on the x-axis versus the height of the building. Now I have some standard deviation values written down here. So the first observation we have here, and there's a few things we can take out of this. One, I'll point out that the DE amplification factor is the blue square, and the SLE amplification factor are the kind of green diamonds. So the first observation here is that there's really no correlation between amplification factor and building height. I mean, maybe we could draw a slight line through here, but I don't think there's any real trend, at least that we observed here, between the amplification and height. The second observation is that the MCE divided by DE factor although it varies between 2 and about 3.8, the average here is 2.9. The SLE factor varies from almost as low as 2, it's actually 2.2. It goes up to about 6.4, and the average is 3.6. So this is not surprising that the SLE amplification factor is a little higher than the DE. What is kind of surprising and what's important to point out is the spread. If you look at DE, the spread here, it's much tighter than the SLE spread. In fact, if you do plus or minus 1 standard deviation on the MCE divided by DE results, it goes from 2.3 to 3.5. So that's a pretty tight band. Whereas for MCE divided by SLE, it goes from 2.4 to 4.8. So the spread, just plus or minus 1 standard deviation for SLE, is twice what it is for DE. This would lead to the recommendation that if you are purely trying to proportion your building in the early stages, you should probably use DE results, not SLE. Now, whatever your other feelings are about DE and how applicable it actually is to your building design, it is useful for initial proportioning. Here are the same results for base moment. Now, again, there's no clear relationship between base moment amplification and height. As Tom pointed out, the moment amplification factors are a little bit lower than the base shear amplification, mostly due to expected moment strength and higher mode effects. The MCE divided by DE factors vary from 1.3, note that that's actually less than 1.5 for one of these buildings, all the way up to 2.6 with an average of 2.1. And the SLE results go from 2 all the way up to 7, all the way up to about 6. And the average here is 3.9. And once again, the spread on the DE results is much tighter. Plus or minus 1 standard deviation here is 1.8 to 2.5. So it's a pretty tight band around the average. Whereas for SLE, it goes from 2.4 up to 5.4. So I don't know about you, but I would not want to use those SLE results and have any confidence in proportioning my building. The next case study we looked at, we said, okay, those results are great, but they only tell me about what's happening at the base. They don't really give me an idea of what the amplification looks like with height. So we had the question, does the amplification factor vary with height as you go up and down the building? And also, does it vary based on which particular wall pier you're looking at? We expected some variation, especially due to localized yielding, as the longitudinal rebar starts to yield in one pier, but it's still elastic in other piers. That will help concentrate some strain and some demands in certain elements. There's also differences in relative stiffness between the DE model and the MCE model. Higher mode effects, as Tom mentioned, spectral shape. For example, the DE is typically based on 2/3 MCE, which is uniform risk spectrum, whereas MCE results a lot of the times are done using CMS, so they have a different spectral shape. Boundary conditions that are different between the two models. One might have fixed base, one might have soil springs. And then, of course, there are different damping assumptions. So to study this, we looked at one sample building. It's a 40-story building on the west coast of the US. It's actually one of the case study buildings that we looked at. It is a central concrete core wall with a 5-level basement, and it has a small podium structure on it. This is a floor plan of it. In this case, north is to the left. I highlighted 4 walls here that I'll study in a little more detail on the next slides. But we're looking at a north wall, an east wall, both of which are pretty long shear piers, and then the west wall and the south wall, which are a little bit shorter. It's as I mentioned, it's a residential building with a 7.5-inch concrete PT slab and surrounded by exterior perimeter columns. Here's a comparison of the shear stress ratio for the north and east piers. I didn't include the south and west piers in the presentation because they kind of tell the same story, but those are in the paper. In this case, the shear is expressed as a ratio of F prime C, and there's a couple observations here. One is that if the amplification factor between, by the way, MCE is in yellow, DE is in blue. I've also got SLE here, the dashed black line, but we've kind of ignored it because it doesn't really control anything for this building. But if the factor, say it's 3, based on our previous results, if it were uniform with height, we would expect the two shapes to be the exact same. And we can pretty clearly see that that's not the case. For example, although they're similar through most of the height of the building, when you get towards the base, the MCE results take a dive right around elevation 25 feet, which we don't see in the DE results. This causes the MCE divided by DE factor to take a spike. It goes down as low as maybe 1.5 for the north wall only. The east wall does the opposite. So that's an interesting trend that even within the same building at the same elevation, the results are not consistent between shear piers. They might have an amplification factor of 5 in one pier and maybe it's 2 in the other. This figure is a little bit more telling, I think. This is the actual amplification factor for shear in the shear piers for MCE divided by DE. The vertical dashed line right here in the middle, that's the average of all of them. You can see it's right around 3. It's a little bit over 3, but that's within the range of what we would expect. But there's a huge variation between the different shear piers. I've plotted in color. The 4 colored lines are the walls that I highlighted previously. And then I've actually plotted all the rest of the walls in the building, kind of shaded back in gray. But really the point here is just to show you the big spread between the results. In fact, you can see the north pier, this blue line, right around elevation 25 feet, where I said it dives pretty low. And then the east pier at that same elevation, or close to that same elevation, it actually has quite a bit of a spike. The main takeaway here is it's important to keep this variation in mind when you're proportioning the building. It's not just a simple matter of using 2.5 or 3 and sizing every single wall based on that exact criterion. In fact, you might want to think about where you're expecting localized concentrated yielding, plastic hinging, and build in a little more buffer thickness there. In this case, we saw some pretty big spikes lower in the building, but this is kind of unique to this building geometry. It could be in different locations depending on if you have a podium setback or if you have a change in wall thickness or something like that. So in conclusion, if we were to try and get some takeaways from this, some recommendations based on MCE divided by DE amplification for wall shear, we'd recommend using a factor somewhere between 2.5 and 3.5. For prediction based on SLE results, it's somewhere between 2.5 and 4.5. For predicting overturning moment, which is mostly useful for proportioning your foundation system, the amplification factor is between 1.8 and 2.5. Based on SLE, it's somewhere in the 2.8 to 5.0 range. So where possible, use DE for proportioning. Even if you're in LA or if you're internationally, working internationally where it's not strictly required, it's still worth performing a DE check just to get some initial proportioning completed. And then also keep the variation in mind. Build in some buffer thickness if possible at certain wall locations. For example, at the base of the wall or where you have setbacks, knowing that the amplification factor will not be uniform with building height. Okay, that's all I have. Thank you.
Okay, we have time for a few questions for sure, so a couple minutes.
For the design level earthquakes, I assume that E was 1 for doing that comparison, or I'm sorry, rho was 1?
Yes, rho is 1 for all of those.
What was the R factor for the DE?
It varies by city, but it's typically 5 or 6.
So like for proportioning diaphragms, what would you use the same as, what would you use for kind of checking, like getting a DE diaphragm shear and you want to crank it up to make sure it works? What would you recommend?
That's a really good question. We thought about extending the study and actually pulling out diaphragm demands and comparing those. We would expect it would generally follow the trend of the shear wall, but we don't have specific recommendations like we did for the core walls.
Okay.
What is the family you use in your study?
Typically, it's 2.5% modal damping.
Okay. Oh, yeah, we have time, so.
I have a question regarding the ratio between the base moment you have for MC and DE. I think the average was close to 2. What do you think is the reason why you have such like relatively large number? If you also have a large R value, are you not expecting the modes or the elements to yield at DE?
They are yielding at DE. Generally,
Is it over the strength?
yeah, it's generally overstrength is our understanding of it.
Excellent. Thank you.